Let's do one last example for this section. This is the first time we've introduced an inclined plane. There's some techniques that you can learn that will make doing this a lot easier. So, first of all, this problem, I have a skier that is going down a hill and I'm supposed to find their acceleration. I know that the coefficient of friction between the skis and the snow is 0.10, and I'm supposed to find the acceleration. Now, if you think about it, we know that gravity is what's making this thing go down the hill. And if we draw our free body diagram, we're going to have to include the weight, of course. So I'm going to put that in. And a normal force. We also know that there's friction in this problem. Normally, the first thing I would do in a problem like this is find the components of any force that is at an angle. However, if you notice, the normal force is at an angle and the friction force are at an angle, and yet my direction of motion is down the hill. Now, what would be a lot smarter for me to do, instead of finding the components of those two forces, the normal force and the friction force, and finding the components of the acceleration, the smart thing would be to actually tilt the axis so this becomes the positive x direction, this becomes the negative x direction, this is positive y, and down this way is negative y. This solves a lot of problems for us because we don't want an acceleration that's at an angle. We want an acceleration that's right along the x-axis. It's just going to make our life easier. And if you notice, what that's done for us is it's made the normal force no longer angled. It makes it in the positive y direction. And it makes the friction force acting in the negative x direction. Now the only one that's at an angle is the weight. And so we will have to find the components of that. So the components would be the two, I'm going to do this in color, would be the two vectors that run perpendicular to the surface and parallel to the surface. Be really careful about this, because oftentimes people will make one perpendicular surface and one parallel to the ground, and that's not going to cut it. Okay, now what we need to do is write these in terms of the angle. Now, you could do a little geometry, and I'll let you do it on your own, or maybe you just see this right away, but this 30-degree angle is going to be right here. And so what that's going to do for me is it's going to make it so the vector that points into the surface is the adjacent side. So this is going to become mg cosine of theta, and this guy here is going to be mg sine theta. And by the way, it always works this way. Now, I know this might mess with you a little bit, because in the past, our horizontal, or x component, was always cosine, and our y component was sine. But that's a little different now because of the angle being this angle at the top of the triangle. Okay, the thing that always holds true is that the cosine is for the adjacent vector and the sine is for the opposite vector. So now if I look at this thing in terms of the net force, let's say in the x direction, equals ma, I can look and see that the only force pointing in the x direction is mg sine theta. The only force pointing opposite that is the friction force. And what's it equal to? ma. Now, in the y direction, we're going to have no acceleration because we're not moving in that direction. So what that's going to do for us is it's going to say that the normal force minus mg cosine theta is equal to 0, which means they're equal to each other, right? Fn equals mg cosine of theta. Making some substitutions, we know that the friction force is mu times the normal force. And the normal force we just found out over here is mg cosine theta. So that means the friction force is mu mg cosine of theta. And now we can substitute that up here in our top equation. And let's see what we get. I'm going to scroll down a bit. And this equation up here is now going to become mg sine theta minus the friction force, which we just said was mu mg cosine theta, equals ma. Now, one of the things that stops people a lot when they do a problem like this is they're saying, hey, I can't do this problem. I don't know the mass. But look what happens. I got mass, I got mass, and I got mass. If I divide both sides by m, goodbye mass. Interesting. Turns out that the mass doesn't matter. And my acceleration is going to wind up being g sine theta minus mu g cosine theta. If we factor a little bit, we get that the acceleration is equal to g times sine of theta minus mu cosine of theta. And then we can plug some numbers in. We've got 9.8 meters per second squared times the sine of 30 minus 0.10 times the cosine of 30. And once my calculator is finished doing its job, I come up with an acceleration 4.02 meters per second squared. These inclined plane problems, what they all have in common is that you're going to have to find the components of gravity, of your weight. This business here. The components are going to wind up being the ones in our equations, not the weight itself.